Hello everyone, my name is Hongmin Lai. This talk is entitled Efficient Support of the Scan Vector Model for RISC-V Vector Extension. This is joint work with my advisor, Professor Zhenkun Li. We are from National Tsinghua University in Taiwan. In this presentation, I will first introduce the problem and the motivation of our work, followed by background information about RISC-V vector extension and the scan vector model. Then I will briefly introduce how to program with RISC-V intrinsic and some important features of RISC-V. Next, I'm going to show how we support the vector instructions in the scan vector model with examples. And finally, the experiment result and the conclusion of the work will be presented. RISC-V vector extension is an emerging extension of RISC-V and can be used to accelerate data parallel workloads. To fully utilize hardware resources requires a proper abstraction and an efficient support of it. In this work, we propose an efficient support of the scan vector model for RISC-V. We support the well-known algorithmic model for parallel algorithm called the scan vector model. We exploit the features of RISC-V to achieve performance and scalability. With our support, parallel algorithm can be deployed to RISC-V efficiently. The RISC-V vector extension is an optional extension of the base RISC-V instruction set architecture. Unlike the package SIMD extension, RISC-V adds additional 32 vector registers to perform parallel operations. For SIMD extensions, the preferred vector register length depends on the types of workloads that the extensions targets. This results in lots of extensions with different vector lengths and increasing porting effort. To address this problem, RISC-V left the vector length as an implementation-defined constant parameters. RISC-V program get vector lengths at runtime, allowing an RISC-V program to scale across different RISC-V implementation automatically. Currently, the specification of RISC-V is version 1.0 and has been frozen for public review. It is considered stable enough to develop software projects. The scan vector model is an algorithmic model presented by Blalock. It can be used to develop a variety of parallel algorithms. In the scan vector model, there are three classes of vector instructions: the element-wise instructions, permutation instructions, and scan instructions. Parallel algorithms can be developed by this vector instruction and then be deployed to the target machine efficiently. In our work, we use the RISC-V intrinsic API to develop vector instructions in the scan vector model. Intrinsic API works like inline assembly. Developers can have more control to the generated code by writing assembly-like syntax in C language program. Compared to inline assembly, programming with intrinsic is more maintainable and allows compiler to perform further optimization. Here is an example of how RISC-V intrinsic in C looks like. On the left-hand side is an example C program using RISC-V intrinsic API. We can pass variables and get the return value of an intrinsic function just like using normal functions. The corresponding assembly is shown on the right-hand side. We can see that the generated code consists of RISC-V instructions and have a one-to-one mapping to their counterparts. Since RISC-V has implementation-defined vector length, we can use vector length agnostic programming model to develop RISC-V program. Vector length agnostic, or VLA, means that the vector length is unknown when developing the program. As a result, we should treat the vector length as a variable. To get this value, RISC-V provides a configuration setting instruction vsetVL. It takes total numbers of elements to be processed and returns the actual number of elements that the hardware will handle. This instructions comes in handy for a common technique in parallel program called strip mining. When using VLS style for strip mining, we need an additional loop to handle the remaining elements. This results in larger code size and performance anomaly. While RISC-V with SpaceSat VL can eliminate this remaining loop. RISC-V also provides selective execution with vector masking. Vector instruction can mask off elements specified by the mask value stored in the vector register V0. This can save the encoding for specifying the mask register. There are two different policies for determining the value of the masked off elements. One is mask undisturbed policy, and the other is the mask agnostic policy. The example at the bottom shows the difference between these two policies. When V3 adds V2 values, the mask off elements remain the same if using the mask undisturbed policy. However, it will be undefined value or agnostic value when using the mask agnostic policy. This policy enables expressive semantics and optimization opportunity. Another important feature of RISC-V is the vector grouping done by the vector length multiplier register. By giving different values to the length multiplier LMO, we can group multiple consecutive vector registers together. Then, we can call this vector register group by the first register name. For example, if we set LMO to 2, then V0 means the vector register group of V0 and V1, while V2 means the vector register group of V2 and V3. Now I'm going to show how we support the scan vector model for RISC-V. We support three classes of primitive instruction in the scan vector model: element-wise instructions, permutation instruction, and scan instructions. We also support simple operation that can be implemented by this instruction, like enumerate operation or split operation. Now I'm going to show how these vector instructions are implemented in RISC-V. For demonstration purpose, details are simplified. Full source code of our implementation using RISC-V intrinsic are provided in a paper. Now we are going to demonstrate how the element-wise instructions are accelerated by RISC-V step by step. Take the p-add instruction as an example. It adds two vectors A and B together. First, we use the vector load instructions VLE to load elements to the vector register. We can load normal length VLAN bits. In this case, we can only load 4 elements in one strip mining iteration. Second, we add two vectors in register together by the vector add b-add instruction. Finally, we store the result back to the memory by the vector store instruction VSE and continue the next strip mining iteration. Here is an example of permute instructions. The permute instruction takes a source vector and an index vector. Then it permutes elements in the source vector to their corresponding destination. First, we load elements to vector registers. Second, we multiply a value by 4 with the logical shift-led instruction VSLL because the element has 4 bytes. Finally, we scatter the source value to destination based on the address offset by the indexed store instruction. The scan operation, also called all-prefix sum, takes a binary operator and an array as an input. After the operation, it outputs an array consisting of all the prefix sum. Depending on the output array, there are two types of scan operation. One is the inclusive scan and the other is the exclusive scan. The inclusive scan sums all the prefix element in itself, while the exclusive scan only sums its prefix together. In our work, we support the inclusive scan. Unlike element-wise operation, scan operation has dependency between elements. Here is an example of scan instructions, the plus scan instruction. First, we load the element by the vector load instruction. Second, we slide up the vector by one offset and get a new vector. Third, we add the original vector and the new vector together. Now, every element sums their previous elements. Then we do another iteration. This time, we slide up the vector by 2 offset. And we add 2 vectors together again. Now the result vector is the inclusive scan vector. Finally, we store the result back to the destination vector. It is worth noting that we need to pass the last value of a streamlining iteration to the next iteration as the carry value to accumulate the prefix sum. Segmentic scan operation split one array into several segments that can execute scan operation independently. To represent the segment, we use head flag representation to denote the starting point of different segments. Here is an example of segmented scan instruction, the segmented plus scan instruction. It will be easier to demonstrate the in-register phase of the segmented scan instruction with larger vector register. So in this example, the VLAN is double, comparing to previous examples. For the segmented plus scan, first we need to load elements to register just like other instructions. We also need to load the head flags. Then we compute the inverse of the flag to get the source of the initial mask. The third and the fourth step is the same as the scan instruction, except that vector add is masked off. Next, we need to update the mask by slide up and the bitwise logical OR. In every iteration, the slide up offset is the same for summing up elements and updating mask. It's worth noting that the in-register phase requires log n iteration to complete, where n equals to number of elements in the register, which is VL. In our experiment, we use LLVM to compile C program with RVV intrinsic, and we use RISC-V GNU toolchain to link and generate the final executable. Finally, we execute the program on the RISC-V simulator called Spike. We configure Spike to perform different experiments. There are 2 parameters, VLAN and ELAN. VLAN is the number of bits in a single vector register, and ELAN is the maximum size of a vector element that any operation can produce or consume. The value must be a power of 2. We set VLAN to 1024 when we test the performance, and 512 and 256 when we test the scalability. We set ELAN to 64 to process 64-bit data types. Here is the experiment result. We compare the dynamic instruction count of p-add and plus scan instruction to their sequential implementation. The p-add can achieve 21 times speedup, while the scan can achieve 2 times speedup. Since the scan instructions had more dependencies between elements, it didn't parallelize as good as element-wise instructions. We also conduct experiment on the segmented plus scan. It got better speedup than the unsegmented scan instruction. Finally, we compare sorting algorithm developed upon our support of the scan vector model to the standard CQ sort. We get better performance when the number of elements is larger than 1000 and can achieve 4 times speedup. Using vector grouping feature of RISC-V can increase the vector register length and result in better performance. However, larger LMO is not always a better choice. The table on the right-hand side shows the ratio of the speedup to the current LMO. Ideally, the value is 1, indicating the performance can scale across different vector grouping configuration. However, this is not always the case. In our experiment, when LMO getting larger, the speedup does not keep up with it. For n equals 100, using largest LMO even takes more instructions to complete. This is because the total number of vector registers does not change. So larger LMO will take up all the registers and cause register spilling. Hence, more instructions count. However, when number of elements is large enough, larger LMO achieve the best speed up. We also experiment this performance scalability over different VLAN. We take segmented plus scan and p-add to execute on different VLAN configuration. The baseline is VLAN equal to 128. The experiment shows that our support can scale across different VLAN, and that element-wise instructions scale better than scan instructions. Finally, here is the conclusion of our work. We support vector instructions and operation in the scan vector model. With our support, parallel algorithm can be developed by these instructions and can be deployed to RISC-V efficiently. Our support of the scan and segmented scan can achieve 2.85 and 4.29 speedup respectively. With further LMO optimization, we can improve the previous result to 21.93 and 15.09 speedup. Thanks for listening.